If our eyes were sensitive gods, and if the radiation was not absorbed by the atmosphere, the sky above us would seem more interesting than it is now. Every day, you would notice bright flashes that somehow appear at any point in the sky and quickly disappear. Some flashes would be so bright that they would momentarily overshadow everything, even the sun. Perhaps it would be challenging for us to get used to such occurrences, but this is what gamma astronomy has been observing for decades. Gamma flashes are the most powerful things ever seen in the universe, and they occur constantly. Nothing in our galaxy shining more intensely than this event, and it lasts only a few seconds. It emits as much energy in that short time as the sun generates during its 10 billion year lifespan. Of course, scientists are trying to explain the source of such energy, but as often happens, many questions remain unanswered. An unexpected discovery. Long before the first gamma rays of cosmic origin reached our detectors, scientists knew that the universe must produce them. Within various processes, the interaction of cosmic rays with interstellar gas was expected to generate bursts of radiation, including in the gamma range. Therefore, studying the universe in this wavelength was considered a promising branch of astronomy in the first half of the 20th century. However, it was challenging to expect the development of gamma astronomy on the Earth's surface, since our beautiful atmosphere absorbs radiation of such wavelengths. So the first gamma photons of extraterrestrial origin were discovered by astronomers with the advent of the space era in the early 1960s. NASA launched the first gamma telescope, Explorer 11, into low Earth orbit, which managed to detect fewer than 100 gamma radiation photons originating from astrophysical sources. However, no one expected to see what was accidentally discovered, not even through scientific equipment designed for such purposes. The thing is, gamma radiation is also a product of nuclear bomb explosions. Therefore, in the late 1960s, the USA launched a series of Vela satellites into orbit to detect similar bursts. Americans suspected that the Soviets would conduct secret tests of their bombs, despite having signed a treaty banning such experiments. As it turned out, on July 2, 1967, the first burst did indeed appear, but its nature was challenging to explain through any nuclear weapon signature. Furthermore, more Vela satellites recorded an increasing number of bursts, which led to the need for a team of scientists from the research laboratory in Los Alamos to investigate their origins. The team managed to identify the origin of at least 16 bursts, which turned out to have no connection to Earth or the Sun. Through meticulous research and verification, their findings were published in the Astrophysical Journal in 1973 in an article titled Observations of Gamma Ray Bursts of Cosmic Origin. This marked the beginning of the gamma ray burst era and hundreds of subsequent studies attempting to explain their nature. Early speculations about the nature of the bursts involved two main camps among scientists. Some believed that the bursts originated from the outskirts of the Milky Way, while others preferred cosmological explanations, suggesting that the sources of radiation could be located deep in space. However, it was only in 1991, with the launch of the Compton Gamma Ray Observatory, that it became clear that the bursts are evenly distributed in all directions. This argument goes against the idea that the sources originate from our galaxy because they would likely be concentrated in the galactic plane, or at least near it. Instead, the bursts occur everywhere, and each time in a new location, appearing unexpectedly and disappearing rapidly. The duration of the bursts varies from just fractions of a second to several minutes, with a typical burst lasting only a few seconds. This is remarkably fast, even in the context of our familiar life, and in the timescale of the cosmos, it is minuscule. Some scientists suspected that the rapid temporal variability indicated that the sources of the bursts must be compact and emitting jets that move at speeds close to the speed of light. It was logical to assume that such jets would interact with the interstellar materials surrounding them, creating shock waves. This might appear like a gamma ray burst's afterglow, but in the form of lower energy emissions, such as X-rays, ultraviolet, and optical radiation, as well as on longer wavelengths. If astronomers could observe this afterglow, they might be able to understand more about the origin of the bursts and their distances. However, the early searches for afterglows were unsuccessful because the next burst could occur anywhere, and it was challenging to quickly point any other telescope sensitive to shorter wavelengths in that direction. Such a telescope is known as a satellite, and it was the satellite that succeeded where others failed. In 1997, it detected the gamma-ray burst GRB 970228. However, apart from the gamma-ray detectors on board, it also had a camera that could see in X-rays. This camera was the first to capture the fading afterglow that lasted for several days after the initial burst. Subsequently, with the help of ground-based telescopes, astronomers were able to identify a very faint galaxy where the afterglow was observed. Unfortunately, due to its low brightness, it took several more years to precisely determine the distance to this galaxy. Nevertheless, the discovery of another gamma-ray burst registered by the satellite in Timashka was a true breakthrough. Finally, it became possible to measure the redshift of the object that could be the host galaxy of this burst. It turned out that the burst had traveled to us for approximately 6 billion years, indicating that it indeed occurred in a very distant and ancient galaxy. Taking this colossal distance and the brightness of the bursts into account, astronomers finally understood the tremendous energy they deal with. The most powerful short-duration bursts surpass the brightness of an ordinary supernova by hundreds of times. In fact, their average brightness at such vast distances is comparable to a star within the Milky Way. However, the condition is that the source of the burst is billions of light-years away from Earth. As I mentioned earlier, a typical gamma-ray burst emits as much energy in a few seconds as the Sun produces during its entire 10 billion-year lifespan. This energy is highly focused, allowing us to observe only those bursts that are directed squarely at us. On average, astronomers observe approximately one burst per day, but according to their calculations, about 500 similar explosions do not reach our detectors during the same period. This raises the question of the source of these long-duration energetic events, which remains a challenging topic. If we examine the curves around these phenomena, they appear quite different, much like the fingers of deputies. Seemingly, no two gamma-ray bursts are alike. Some curves seem chaotic, with erratic jumps in brightness, while others begin as a small flash, which seems like a precursor to the appearance of another, more powerful burst that emerges after a few seconds. Nevertheless, gamma-ray bursts do have at least one characteristic that astronomers use to classify them: their duration. So-called long bursts are more prevalent and last from 2 seconds to several minutes, while short bursts have durations of less than 2 seconds and often vanish within milliseconds after their appearance. Long bursts are better studied since they make up about 70% of all known bursts. Their longer duration allows astronomers to point other telescopes towards the burst's location for follow-up observations after the initial flash. This helps in searching for the afterglow and potential galaxies from which the burst likely originated. Typically, the bursts come from galaxies that are very young and undergoing intense star formation. These galaxies serve as ideal places for the birth of massive stars, which are known to explode exceptionally powerfully. In many cases, astronomers have found supernovae in the same location shortly after gamma-ray bursts, and this correlation is difficult to attribute to mere coincidence. For example, supernova SN 1987A appeared after one such gamma-ray burst, signaling the first hint that these two most extraordinary explosions in nature might be connected. However, the energy released during a gamma-ray burst is so immense that it is essentially equivalent to the transformation of the entire mass of the Sun into pure energy within seconds. A typical supernova would hardly be capable of accomplishing such a task. To explain these bursts, something more powerful is needed, such as a hypernova. These explosions are about 100 times brighter than supernovae and are thought to be produced by extremely massive stars rotating at exceptionally high speeds with strong magnetic fields. When a star is at least 30 times more massive than the Sun, it burns through its hydrogen reserves until it can no longer withstand its own gravitational force, causing its core to collapse. It then forms a black hole, losing its core in the process. The star begins to fall into the black hole with all its material, and the black hole gladly devours it. However, in stars that rotate exceptionally fast, the material falling into the black hole swirls around it at tremendous speeds, like a frenzied vortex. Inside the star that is about to die, a black hole with an accretion disk emerges. Overheated plasma is trapped in the magnetic fields, which twist it into jet-like streams resembling an electromagnetic cannon. These streams of gas break through the hapless star's poles and shoot out into space, draining the star and forcing the plasma flows to move in narrow jets that tightly focus the energy. If these jets are precisely directed towards the Earth, we observe this energy release in the form of a burst. However, if the burst is directed in any other direction, the gamma-ray burst will remain undetected. This model of a massive star's core collapse is currently the most accepted explanation for generating gamma-ray bursts. However, it only explains the sources of long-duration bursts. Explaining the sources of short-duration bursts is much more challenging. This is mainly due to their rapid and brief nature, ranging from a few milliseconds to 2 seconds. It is known that short bursts are usually dimmer by a factor of 10 than long bursts, but they emit higher energy gamma-ray radiation. This suggests a different nature for their source. Before 2005, no afterglows of short bursts were detected, earning them the name dark bursts, as they left no afterglow. However, everything changed with the launch of NASA's Swift gamma-ray burst mission, possibly one of the most successful space missions ever. Swift, in general, has been one of the most successful space missions launched. Was launched back in 2004, and it has been operational for 19 years now. Besides its highly sensitive gamma-ray detectors, the observatory is equipped with X-ray and optical telescopes that can automatically and swiftly turn towards a new gamma-ray burst and study it after the burst. Currently, Swift works in conjunction with another space gamma-ray telescope, Fermi, launched in 2008. By the way, the animation of gamma-ray activity in the sky, captured by Fermi over the past year, shows that most of the purple dots are emissions from blazars, also known as quasars, which are jets pointing directly towards us. The yellow spot represents the sun moving across the sky during this year. Thanks to the work of these telescopes, astronomers have finally managed to observe that at least some short-duration gamma-ray bursts have an afterglow that quickly fades away. They have also been able to localize the sources of their origin, and some of them were found not to be associated with regions of active star formation. For instance, the gamma-ray burst on May 5, 2009 was found to originate from elliptical galaxies where star formation practically does not occur, and stars in such galaxies are mainly old and less massive, not prone to exploding as supernovae. However, this aligns with the popular idea among scientists that short bursts do not originate from massive star explosions, but from the collision of two neutron stars or a black hole and a neutron star. Confirmation of this idea was captured by the Hubble Space Telescope when it managed to detect the flash of a so-called kilonova immediately after Swift detected another short gamma-ray burst. A kilonova is a powerful explosion resulting from the collision of neutron stars or black holes with similar stars, thus supporting the connection between gamma-ray bursts and neutron stars. This link was further strengthened by observations from the LIGO Observatory, which specializes in studying gravitational waves. In 2017, LIGO detected a series of gravitational waves caused by the merger of neutron stars, providing even more reliable evidence for this connection. Interestingly, at the same time, the Fermi Gamma-Ray Space Telescope recorded a short gamma-ray burst in that part of space. It appears that the remnants of neutron stars after a collision rotate around the newly formed black hole, similar to what is observed in the model of long-duration gamma-ray bursts. The rapid rotation of matter in the accretion disk also generates powerful short gamma-ray bursts. Moreover, last year, two independent groups of astronomers observed evidence of a kilonova immediately after a long-duration gamma-ray burst, suggesting that this type of gamma-ray burst may also be caused by neutron stars. Overall, this indicates that we still do not fully understand the nature of the most powerful explosions in the universe. Now let's finally talk about the most powerful burst in the history of observations, the record holder for the brightest flash ever observed. This event, named GRB 22109, occurred on October 9, 2022. The burst was so intense that it was immediately dubbed the brightest of all time. It lasted quite a long time, about 7 minutes, and was so bright that it overwhelmed most gamma-ray instruments in space, making it challenging to determine its actual intensity. Eventually, American scientists had to reconstruct this information using data from the Fermi telescope. By comparing the emission from GRB 22109 with the previous record holder that occurred in 2013, they found a colossal difference in brightness. Analyzing this burst and comparing it with thousands of previous ones, scientists concluded that such an event happens approximately once every 10,000 years. Thus, this energy burst is likely the most powerful in the history of our civilization since records began. After the burst, it was incredibly bright, and numerous observatories worldwide observed it. Astronomers were expecting to witness a kilonova associated with the burst, but so far they have been unsuccessful in finding it. One possible reason for this is that the burst occurred very close to the plane of our galaxy, so dust clouds may simply obstruct the light from reaching us. As a result, astronomers hope to see it using James Webb Space Telescope, which can see through clouds in the infrared range of the electromagnetic spectrum. Interestingly, when the radiation travels through our galaxy, including through gas and dust clouds, it scatters, creating X-ray reflections. In the X-ray range, this looks like expanding rings from the location of the gamma-ray burst. The European Space Agency's Newton X-ray telescope has detected around 20 such rings, each formed by a separate cloud of gas and dust. According to NASA's article, the way X-ray radiation scatters depends, in part, on the distance to these clouds. The widest ring in this image comes from a cloud about 13,000 light-years away, and the inner ring comes from a cloud at a distance of 61,000 light-years, which is from the other side of our galaxy. By the way, this is only the 7th gamma-ray burst that shows X-ray rings, and the number of these rings is 3 times greater than what was previously observed. Is there a threat to Earth? Unlike most gamma-ray bursts observed in very distant galaxies, the latest record holder is perhaps an exception. It occurred at a distance of approximately 2 billion light-years from us. That's still very far away. However, could something similar happen in our galaxy? But it's better if they continue happening in galaxies billions of light-years away from us. If something similar were to happen relatively close, the intense radiation, at the very least, could deplete our ozone layer, leading to catastrophic problems associated with harsh ultraviolet radiation from the sun. That's why the idea that the Ordovician Silurian extinction could have been caused by a gamma-ray burst around 450 million years ago is so popular. However, in reality, there is not substantial evidence supporting this hypothesis. Most paleontologists will tell you that this extinction is more likely related to climate changes on the planet or a reduction in oxygen levels in the oceans due to geological processes. So, even if a gamma-ray burst were to occur someday in our galaxy, the question remains open. Moreover, all known gamma-ray bursts originate from ancient, metal-poor galaxies, and it is uncertain whether modern, metal-rich galaxies, like the Milky Way, can produce such explosions. Even if they could, the likelihood of the gamma-ray bursts hitting Earth directly seems almost impossible to me and some others in the world, despite the occasional internet scare. If there was one of the brightest and most destructive phenomena in modern space, it would be a supernova explosion. LMC N49 is a supernova that exploded about 5,000 years ago in the Large Magellanic Cloud, a companion galaxy to our Milky Way. Unfortunately, it cannot be seen from Earth because it is about 160,000 light-years away. However, if the supernova had been closer to Earth and existed during ancient times, such as the Sumers in the southern hemisphere or ancient Egypt, it would have been recorded as the first supernova explosion in history. LMC N49 is believed to have been a very bright and massive unstable star. Supernova explosions are a profound phenomenon, and one that is clearly displayed is G1.9 plus 0.3. This supernova explosion is the most recent of this type of event to occur in the galaxy. The supernova exploded in 1899. Imagine, the the 20th century was a time of dramatic scientific and technological advancements, as well as social and political upheavals. Now, well into the 21st century, there has not been a single supernova explosion among the trillions of stars in the galaxy during this period. Is the universe laughing at us? Scientists sometimes have such thoughts, and G1.9+.3 is one of the pieces of evidence. Although the supernova explosion occurred at the turn of the 19th and 20th centuries, we did not realize it. In fact, the supernova was hidden in dense gas and dust clouds near the center of the galaxy, and even with the technology of the time, we could have obtained a vast amount of valuable information. Needless to say, our technology has improved dramatically over the past 123 years, and that technology is being used to investigate supernovas that are difficult to observe in other galaxies. Supernovas appear as neutron stars or black holes covered in gas and dust clouds, just like other supernovas. Interestingly, these clouds continue to expand at an enormous speed of 15,000 kilometers per second. At present, the clouds have expanded to a size exceeding 2.5 light years. This hypothesis may or may not be confirmed, depending on whether a similar presence is found near Earth. Located in the X-ray region, the constellation of Andromeda is one of the brightest celestial bodies, emitting very powerful radiation that can be likened to the Chernobyl disaster. As you may know, the radiation zone, located 7,000 light-years away from the Sun, is the remnant of a supernova. The gas cloud in the constellation of Andromeda, known as RxJ0822-4300, is actually the core left over from a neutron star after a supernova explosion. After comparing the velocities of this object and the surrounding stars, it was found that it was moving at an exceptional speed compared to other objects that had been measured, with an estimated speed of 1,300 kilometers per second, moving away from the point of the supernova explosion. The reason why neutron stars reach such speeds is unknown, but it could be a unique characteristic of the explosion. It is also important to consider that the explosion occurred about 5,000 years ago, and the acceleration may have decreased over time. How fast was it going at the beginning? The supernova SN 154, which gave birth to the Crab Nebula, became famous for this reason. First, scientists discovered the Crab Nebula and then calculated that the supernova that created it exploded around the 11th century. Afterwards, scientists discovered a record of a bright star suddenly appearing in the same place where the Crab Nebula was discovered in ancient Chinese documents, which was a great triumph in astronomy. Behind this shining success, there was another quiet supernova. SN 1006 exploded 48 years before SN 054 and was even brighter and better documented in historical records, while only the Chinese realized the significance of SN 1054. However, SN 1006 was recorded in documents from various regions of the Eurasian continent, including Switzerland, Egypt, and China. Arab astronomers reported that the celestial body shone brighter than Venus, while European monks claimed that the star not only changed in brightness, but also in size, expanding or contracting, and sometimes even disappearing completely. The explosion of SN 1006 occurred in this vicinity, and even after a millennium had passed, the diffusion rate of the gases released by the explosion was still remarkably high, at a speed of 9,000 kilometers per second. The power of the explosion must have been beyond imagination. There is another supernova that has expanded human knowledge of the universe, and that is SN 572, which occurred in the Cassiopeia constellation in 1572. Like the heroine introduced earlier, this supernova was observed throughout the Eurasian continent, from the Korean peninsula to England. The history books of Europe and the Arab East contain detailed descriptions of this remarkable star. The name of this supernova comes from the famous Danish astronomer Tycho Brahe. However, he was not the first person in Europe to discover this supernova, nor was he the first to record its appearance in detail. Nevertheless, he studied stars in much greater detail than any other scholar in the world at that time. He succeeded in measuring the parallax of this celestial body, which was a significant accomplishment at the time. According to the observation methods at that time, Saturn was considered to be the farthest planet from the Sun or the Earth. However, Through simple calculations, he discovered that this supernova was much farther away than the Moon or Saturn. In this way, humanity first became aware of how vast the universe is and how far stars are from us. There is another excellent discovery that has advanced astronomy. It was made by two contemporary British scientists, Thomas Diggers and John Dee, who discovered the same nova. Using data from Tycho Brahe and their own measurements, they overturned the 1,000-year-old image of stars being located on celestial spheres and speculated that stars would be spread throughout the universe. Perhaps no astronomical phenomenon has had such a significant impact on the development of scientific knowledge as Tycho Brahe's supernova. Furthermore, compared to the standard of the nova, there is nothing particularly exceptional about it. Scientists discovered that this celestial body was the result of a white dwarf star exploding in a close binary system. This is one of the mechanisms for supernova explosions, similar to when a massive and bright single star explodes at the end of its life. Another star forming a binary system was also discovered. This star, similar to the Sun, is surrounded by clouds formed by the explosion. Supermassive black hole is the largest known genius among scientists and probably the rarest celestial body. Supermassive black holes typically exist in one galaxy, but not in all galaxies. Hello everyone, here is where these supermassive black holes come from. Let's find out together, starting now. According to existing astronomy and physics, it is known that standard black holes appear when particularly bright and massive supernovas explode. Theoretically, the mass of these black holes ranges from 30 to 50 times that of the Sun, but in reality, there are many that are much lighter. Black holes with hundreds or thousands of times the mass of the Sun have not yet been discovered, and only a few candidates have been proposed. This is known as the intermediate mass black hole problem. The main character of this discussion is the supermassive black hole, which has a mass of tens of thousands to millions times that of the Sun. Its origin is one of the most interesting problems in astronomy and physics. In reality, there are no stars of this size, so where did they come from? The relationship between supermassive black holes and galaxies is also fascinating. These black holes are typically found in the center of galaxies, but the existence of galaxies without supermassive black holes is known. However, supermassive black holes without galaxies have not yet been confirmed. The formation of galaxies and supermassive black holes is a problem similar to the chicken and egg problem. Which came first, the supermassive black hole that gathered matter around it, or the galaxy that formed first and had a black hole at its center? There is still no consensus on this issue. So where did they come from? The biggest problem in the formation of supermassive black holes is that it is not enough for a massive amount of matter to gather at a single point. To increase the mass of a black hole by having a large amount of matter fall into its singularity, it must rotate very slowly. Otherwise, an accretion disk will form around the black hole, and that will be the end of it. Of course, it is possible that the matter in the surroundings could be consumed by a black hole, but it is not very common for it to become a supermassive black hole. To understand the most likely explanation for the formation of these supermassive black holes, we need to look back in time to the distant past, around 550 million years after the Big Bang, during a period known as the Dark Ages. During this time, the universe was filled with hydrogen and helium and was not yet transparent enough for light to pass through. It is believed that the first stars began to shine during the end of the Dark Ages and the following cosmic dawn. As the first stars appeared, matter was consumed and transformed into starlight, gradually making the universe more transparent and bringing it closer to its current state. Generally, the universe during the Dark Ages was a cradle of a giant star, meaning it was a gas or dust cloud where new stars were born. The existing theory is that dark matter actively participated in this process. As dark matter gathered material through gravity and began to surround it, galaxies were formed in no time. At the center of this fence, the density of material is very high, and it is said that primitive stars, which weigh more than 20 times the mass of the Sun, were formed massively at this time. For various reasons, these stars seem to have been very unstable and began to collapse rapidly without exploding. When a supernova explosion occurs, it collapses and becomes a black hole or neutron star. Although it is only a tiny fraction of the matter that was concentrated in the building, when a primitive star collapses, it becomes a black hole in its entirety. Then, these black holes merge, creating a supermassive black hole. Some modifications have been added to the theory through recent research. Many scientists currently believe that there was no merger between black holes, but instead a single primitive star with a vast mass, ranging from tens of thousands to millions of times the mass of the Sun, was formed in the galaxy. It is difficult to imagine what process might have taken place, since such stars do not exist in the universe today. Perhaps these primitive stars began to collapse silently for only a few thousand years. Although this hypothesis seems to make sense, there are several unexplained phenomena. One of them is, as mentioned earlier, that most of the supermassive black holes have masses of hundreds of millions or billions of times that of the Sun, not just thousands of times. For a black hole to become this massive, according to the hypothesis of a collapsing primitive star, it must absorb an enormous amount of matter in a very short astronomical period, many millions of times its own mass. However, in reality, black holes do not continue to grow infinitely because the surrounding matter is almost exhausted. The remaining matter becomes part of the accretion disk and does not fall into the black hole. The first black hole was hypothesized to solve problems with existing theories, and scientists attempted to use new theories, such as the primitive black hole theory. The key point of this theory is that some black holes were not originally related to stars and never were stars. These black holes are believed to have formed shortly after the Big Bang. At that time, the universe was very hot, dense, and rapidly expanding. In this situation, the space itself was moving in a different way from today. It is believed that the unevenness of space, or pockets of space distortion, may have compressed matter and caused collapse. There were various masses in these primordial black holes. The smallest black hole was only about the size of the Planck mass, which is very small at 1/1,000,000th of a kilogram. This type of black hole may have collapsed quickly and no longer exists. On the other hand, there is a possibility that the largest black hole was thousands of times the mass of the Sun. This is the type of black hole that we find most interesting. These primordial black holes had an incredible density of matter. There is a possibility that it absorbed a massive amount of matter in a short period of time and grew to a size close to that of a supermassive black hole, which then gathered surrounding matter and facilitated the formation of the first galaxies. Currently, no new primitive black holes, supermassive black holes, or new galaxies are formed in the universe due to changes in matter density. However, there are weaknesses in the theory. For example, in a very compact universe, a young supermassive black hole may have grown rapidly, but it is unclear why it did not absorb all or most of the matter. Additionally, it is unclear why the universe entered a dark age in this scenario. Matter did not just scatter throughout the universe, but rather it was originally gathered in galaxies. However, if we assume that the natural formation of supermassive black holes was possible not only immediately after the Big Bang, but also during the following 500 million years, we can solve this problem. Currently, there is no hypothesis that can explain why there are no supermassive black holes present in all galaxies. It is possible to guess that this could be due to a lack of matter in dwarf galaxies. But even in the Triangulum galaxy, the largest in our local group, there are no supermassive black holes. Therefore, a theory that can explain all of these phenomena will emerge in the future. Stars, planets, and cosmic matter, bound together by gravitational forces, form some of the most massive objects in the universe, galaxies. The exact number of galaxies remains unknown, but it is estimated to be several hundred billion, and that's only within the observable part of the universe. Despite galaxies being astronomically distant from one another, they sometimes collide. Such collisions are truly spectacular events on a grand scale. Cosmic evolution. In the universe, there are galaxies orbiting around a common center of mass. In such systems, there's a central giant galaxy with several satellite objects. During their evolution, if the orbits of smaller galaxies do not match, they all start to revolve around this center. However, if galaxies have identical orbits, they will merge into one large system, while the smaller object gets torn apart. Astronomers observe such collisions quite frequently. It is believed that the Andromeda galaxy also collided with a smaller galaxy in the distant past. Similarly, our system has also absorbed smaller galaxies. But if astrophysicists claim that the universe is expanding, why do galaxies collide? And all because the expansion of the universe is happening slowly. Galaxies in clusters and superclusters experience gravitational attraction towards each other and move at speeds of hundreds of kilometers per second. The cosmological expansion reaches such magnitudes only at distances of tens of millions of light years, which is hundreds of times larger than the sizes of galaxies. Therefore, within clusters, galaxies do not notice the expansion of the universe. They move and collide as if it doesn't exist. However, no matter how common such interactions may be, astronomers rarely manage to capture dynamic images of colliding galaxies, like the ones Hubble captured. ARC 282 consists of the spiral galaxy NG69 and its smaller companion, IC 1559. They both have highly active cores, serving as powerful sources of radiation. The activity of ARC 282 is associated with the black holes located at their centers. Tidal interaction processes have led to a redistribution of matter within the galaxies, providing the black holes with abundant food. The galaxies have also formed a connecting bridge, which is visible in the Hubble image, consisting of elongated gas and dust affected by tidal forces. And that's not all. The Hubble Space Telescope also took a series of photos of two merging galaxies in the VV689 system, which astronomers have named the Angel's Wings. Unlike random visual alignments of galaxies that only appear to interact from Earth's perspective, these two galaxies in VV689 are in the midst of a collision. This galactic interaction has made the VV689 system in the constellation Leo nearly symmetrical, and now they resemble huge galactic wings. Another well-known space telescope, the James Webb, also captured interesting images. The star cluster in the Cartwheel Galaxy was formed as a result of a collision with a satellite galaxy. The Cartwheel Galaxy has two rings that expand outward from the collision center, much like ripples in a pond after a stone is thrown in. Due to these distinctive features, astronomers refer to it as a ring galaxy. It has a less common structure compared to spiral galaxies like the Milky Way. In the next two galaxies shown in the cosmic image, they pass through each other, leaving a bridge of young blue stars between them. The head-on collision between the two galaxies showcased an object of triangular shape where thousands of stars were born. This image was captured by the Hubble Space Telescope, as reported by NanoWork. Astronomers speculate that the galaxies passed through each other, triggering a fiery burst of star formation in a unique shape in NGC 2445, where thousands of stars ignite. This galaxy is rich in gas, the fuel from which stars are created, leading to its star-forming abundance. However, the new galaxy has not managed to escape the gravitational grip of its partner, NGC before. The galaxy has pulled gas from NGC 2445, creating the peculiar triangle of newly formed stars. As we can see, these interactions can appear stunningly beautiful. In the search for dark matter, but it is not only the beauty that fuels scientists' curiosity. As early as the 1970s, serious arguments emerged in favor of the idea that galaxies contain so-called dark halos, apart from stars and gas. Theoretical arguments arose from considerations of the stability of the stellar disks of spiral galaxies, while observational evidence came from the large, non-decreasing rotation velocities of gas at the far edges of galactic disks, where there are almost no stars, and therefore the rotation speed is determined through gas observations. If the entire mass of a galaxy was primarily contained in stars, then the orbital velocities of gas clouds located beyond the stellar disk would decrease as the distance increased. This is observed in the planets within the solar system, where the mass is primarily concentrated in the Sun. However, in galaxies, this is often not the case, which indicates the presence of some additional massive and extended component whose gravitational field imparts high velocities to the gas clouds. The situation was partly clarified when massive dark halos were introduced into the mathematical model of galaxies. These dark halos do not contribute to the galaxy's overall luminosity and are only evident through their gravitational influence on the stellar subsystem. One way to obtain information about the structure of dark halos is by studying extended structures that form around galaxies during their interactions. For example, sometimes, during a close passage, one galaxy steals gas from another, winding it around itself in the form of an extended ring. The existence of extended polar rings can only be explained if the mass of the dark halo is approximately twice that of the luminous matter in the galaxy. Tidal tails also serve as reliable indicators of the presence of dark matter in the peripheral regions of galaxies. Perhaps the first evidence of hidden mass was obtained as early as 1933, when the astrophysicist Fritz Zwicky noticed that galaxies in the Coma cluster were moving faster than expected, implying the presence of some invisible mass that kept them from flying apart. The nature of dark matter remains unknown, so it is often referred to as some abstract cold dark substance that interacts with ordinary matter solely through gravity. However, due to its significant mass, it acts as the active background on which all scenarios of structure formation and growth in the universe unfold, while ordinary matter passively follows the proposed scenario. These ideas form the basis of the so-called hierarchical clustering scenario. According to this scenario, primary density fluctuations of dark matter arise due to gravitational instability in the early universe and then multiply by merging with each other. As a result, numerous gravitationally bound dark halos are formed, differing in mass and angular momentum. Gas collapses into the gravitational wells of these dark halos. This process is called accretion, leading to the formation of galaxies. The history of mergers and accretion of each dark matter clump largely determines the type of galaxy that emerges within it. The appeal of the hierarchical clustering scenario is that it describes the large-scale distribution of galaxies quite well. The most impressive numerical experiment conducted within this scenario is called the Millennium Simulation. Astronomers reported its results in 2005. In the experiment, the n-body problem was solved for 10 billion dark matter particles, starting from when the universe was only 120 million years old until the present day. During this time, nearly half of the dark matter had gathered into dark halos of various sizes, totaling about 18 million. Although complete and unequivocal agreement with the observations of large-scale structure has not been achieved yet, there is still much to discover. In 2002, a team of researchers led by Beth Willman began the search for unknown satellites of the Milky Way in the Sloan Digital Sky Survey. The first success came in March 2005, when a dwarf spheroidal galaxy was discovered at a distance of 300,000 light-years from us in the constellation Ursa Major. It became the 13th satellite of the Milky Way, with a record-low luminosity. All its stars emit light comparable to that of a single supergiant star, such as Deneb, the brightest star in the constellation Cygnus. The year 2006 turned out to be exceptionally fruitful for the discovery of satellites of our galaxy, when two other teams of researchers discovered 7 dwarf spheroidal galaxies around the Milky Way. And apparently, this is not the limit. Only recently, astronomers started to discover galaxies entirely devoid of dark matter or containing it in extremely negligible amounts. For example, the dwarf galaxy NGC 1052 DF2, which was discovered a couple of years ago by a team led by Peter van Dokkum from Yale University. Since then, several similar objects have been found, including DF4, located near DF2. These galaxies greatly puzzle scientists who are trying to understand how they could have formed without dark matter, or how they lost it. One hypothesis links their appearance to galactic collisions. In such an accident, the masses of their dark matter can continue their trajectory, passing through each other. However, clouds of ordinary matter experience pressure from each other, slow down, interact, and separate from the dark matter. This scenario is supported by an article published in the journal Nature by van Dokkum and his colleagues. Observations of DF2 and DF4 showed that the trajectories of these galaxies started to diverge from a common point about 8 billion years ago. Moreover, other dark matter-poor dwarf galaxies also started moving along with them. Today, DF2 and DF4 are part of a chain of about 7 to 11 such objects, that located at a distance of about 70 million light-years from us. On the scale of star clusters, dwarf galaxies, and galaxies, collisions and mergers are constantly happening. Even our Milky Way is currently disrupting the Sagittarius dwarf spheroidal galaxy, which is its satellite. And in the future, this relatively small cosmic body, with only 1% of our galaxy's mass, will be completely absorbed. Looking further into the future, we can expect a collision and merger with the large Andromeda galaxy. According to scientists' predictions, the Milky Way and the Andromeda galaxy will collide in about 4.5 billion years. And quite soon, in 3 billion years, Andromeda will approach us so closely that the stars of its galaxy will be visible to the naked eye. What will this collision look like? Thanks to the Hubble telescope's image, we can now visualize what the merger of the Milky Way and Andromeda will look like from the outside. A group of 3 galaxies, collectively named NGC 7764A and located in the Phoenix constellation at a distance of 425 million light-years from Earth, serves as a model for this scenario. Scientists are already running simulations of the collision between the Milky Way and the Andromeda Nebula on supercomputers. Data indicates that the Milky Way has absorbed smaller neighbors in the past. For example, some dwarf galaxies and globular star clusters were destroyed by tidal forces and transformed into star streams, with their stars likely to be eventually absorbed by our galaxy. Using data from the Gaia Space Telescope, scientists partially answered the question of when the last collision and absorption of a neighbor occurred. Gaia creates a three-dimensional map of the galaxy by measuring distances to stars, enabling scientists to observe their movement directions. This led to the discovery that around 8 to 10 billion years ago, the Milky Way engulfed a sizable dwarf galaxy called Gaia Sausage Enceladus GSE. As an inheritance from the collision, we received about 8 new globular star clusters along with 50 billion new stars. Additional research revealed that GSE was not a satellite of our galaxy, but was moving in a direction opposite to the Milky Way's rotation. Thus, our courses intersected and a collision occurred, rather than a gradual merger. This intergalactic catastrophe provided us with material, forming about 50% of today's halo and 20% of the dark matter halo. The next similar event, as we mentioned before, will be the encounter with Andromeda. Scientists speculate that if the Andromeda Nebula and the Milky Way eventually merge, the resulting new galaxy will have an elliptical shape. It is even given a name, Milkomeda. By that time, the Sun, which might have transformed into a red giant, will be relatively far from the galactic center, since the distance between stars will increase. However, this won't impact us anymore. The observable universe spans an area of approximately 90 billion light-years, and it can be assumed that the part of the universe we cannot observe is much larger. The cosmos is so vast that the human mind is simply unable to comprehend it, at least for now. However, according to some theories, it is possible that the universe is significantly smaller than it appears. According to current estimates, the unobservable part of the universe may be around 20 trillion light-years in diameter. Just imagine, based on the data we have, we can assume that most of the cosmic space should be empty because the amount of matter in the part of the universe we have explored is relatively small. When we gaze into space, we see vast, incomprehensible expanses of icy emptiness. But what if the universe could fit in one atom? It may sound absurd, but don't dismiss this theory too quickly. It is more like philosophical science fiction. It may not be so unbelievable, but first, let's recall what we know about matter. Any matter is made up of the smallest particles, atoms. These tiny building blocks of the universe, as we know it, are so small that even with the help of the most powerful optical devices, we cannot actually see them. Interestingly, we cannot even know with sufficient certainty what they look like. We can only speculate based on scientific theories. However, it is considered a proven fact that atoms cannot be seen with the naked eye. and the fact that atoms themselves consist of smaller subatomic particles such as neutrons, protons, electrons, and quarks is now well established. Atoms are so numerous and small that the body of an average adult human being consists of approximately 7 octillion atoms. To put this number in perspective, it can be represented as a 7 followed by 27 zeros. Just imagine this amount, but the atom itself also has its own structure, a complex structure that allows us to contemplate the incredible theory of the micro-universe. How does an atom look like from the inside? From your high school chemistry class, you probably remember that an atom consists of a nucleus formed by protons and neutrons, and electrons moving around it. This model, proposed by Ernest Rutherford in 1911, was named the planetary model of the atom. Indeed, the analogy between the movement of atoms around the nucleus and the movement of planets around the sun is evident. Moreover, this model has not been refuted and is even confirmed by modern research. It turns out that the movement of electrons is described by the laws of quantum mechanics rather than classical physics. Thus, the smallest particle that forms the basis of matter has a structure similar to that of the solar system. Is this a simple coincidence due to the laws of physics, or does this similarity hide something bigger, something much more fantastic? We will return to this question later. For now, try to answer the question of how many galaxies there are in our universe. It sounds absurd, doesn't it? Such a number cannot be processed even by the most powerful computer, let alone the human brain. But what if I told you that there is only one electron in the entire universe? This hypothesis, called the one-electron universe theory, was proposed by American physicist Richard Feynman, and it sounds like pure fantasy. According to this theory, there is only one electron in the world that moves through space and time so fast that it appears to us as if there are many of them, giving shape to everything we consider to be the entire universe. What do you think of this? Of course, this theory has not found many supporters, but the most interesting thing is that due to the principle of identity, it is impossible to experimentally distinguish one electron from another is impossible. This paradox cannot be refuted. But let's return to the structure of the atom and the incredible theories it gives rise to. Let's try to answer the question of what size objects are. Despite the everyday familiar meaning of this word, the concept of size is quite mysterious and relative. For example, the world around us is adapted to our size because we built it. But with the creations of nature, it's not so simple. Mountains are huge for us. Planets are gigantic to the point of being impossible to comprehend. But for an ant, all forms of life range from simply small to microscopic. However, do ants consider themselves small and understand that they live in a world of giants? Probably not, as their world is just as familiar to them as ours is to us. Compared to cosmic objects, we are even less than microscopic. This thought gives us goosebumps, and it's no wonder that the great master of horror and science fiction, H.P. Lovecraft, promoted the idea of the insignificance of humanity before the face of the boundless cosmos in his works. And now we come to the main question of our video. What if our universe can fit on the tip of a needle? Suddenly, the solar system, and you are just one of the myriads of similar entities that make up some other matter. Rejecting this version is illogical, so we can assume that the same is true for the particles that make up our existence. Entire worlds may also be contained. It turns out that, as one wise man said, infinity is truly limitless. This means that our reality could really be on a subatomic level of a completely different reality. Similarly, entire worlds could also be located on our subatomic level, and so on to infinity in both directions of scale, which sounds incredible, but exploring the incredible is our job. The most interesting thing is that by looking at the universe we know and observing the laws that function within it, we can easily come to the same conclusion. Everything begins with the smallest particles like atoms and ends with colossal celestial bodies and entire clusters of stars, starting with your lunch today and ending with a recently discovered exoplanet. Everything consists of the same building material. Finding the theory of everything, which relates the micro and macro worlds, is the dream of the scientific community. Combining quantum mechanics and classical physics, young scientists may be able to understand the true nature of our universe, even beyond its boundaries. According to one of the most popular versions of the origin of our universe, it began as an infinitely dense and yet small singularity, which then expanded to all known limits. This is called the Big Bang Theory, from something small to something very big. It also seems to correlate quite well with what we talked about today, micro and macro cosmos, but there is an important remark. It's not that it originated from one atom. There was a singularity that gave birth to the Big Bang. Despite its small size, it contained everything necessary for building the entire universe, but calling it the origin from one atom is not accurate. There is also the so-called string theory, an excellent candidate for the theory of everything. The basic idea is incredibly complex and has many interpretations. The theory suggests that the singularity is not a spherical object whose shape and appearance we remember from school, but rather strings or something very similar to them. The relationship between these vibrating strings includes almost all known laws of classical physics, including gravity and quantum mechanics. However, the string theory also has its weaknesses. Although it explains a lot, it begins to stumble when it comes to dark matter, where the string theory starts to sag. But scientists have been working on incorporating it into the theory. In late 2018, Swedish scientists published a new version of the string theory, which suggests that our universe exists on the border of a constantly expanding bubble. This version rejects the familiar 4 dimensions of 3 spatial and 1 temporal, and suggests that our entire universe is just vibrations on the surface of this bubble. What happens inside the bubble, or at a distance from it, remains a mystery. How do you feel about these perspectives? We are just a small civilization in a tiny piece of reality located on the surface of the bubble, which itself could be a part of something much larger. Perhaps our entire world is just a proton or a quark, just a small particle of reality. Why don't we feel it? Does it feel like the components in your sunglasses, which are just plastic? But is it really important to get a definitive answer to this question? Ultimately, we should just be grateful that our vast and shared home called the universe is full of such amazing mysteries. What would happen if there were a black hole in our solar system? First, let's clarify the concept and numbers a little. Known black holes are formed by a vast amount of matter collapsing into a small space, most often from a star, including very massive stars. The typical mass of a black hole that astronomers have been able to detect is at least 3 to 5 times that of the Sun. Of course, if there were such a black hole where we could stand, we wouldn't be orbiting around the Earth. Instead, the Earth would become its satellite, orbiting around it. But in theory, any amount of matter could be compressed into a singularity, creating a black hole. Therefore, for the purposes of this video, we will assume that our hypothetical black hole has a mass similar to that of the Moon. How could such an object come into being? It could be born from some anomaly, or it could have been born for an alien experiment. More accurately speaking, the event horizon of a black hole is very small, about 0.1 millimeters in size. Earth is not sucked into it because black holes behave the same as celestial bodies with the same mass. However, its effect on Earth is very interesting. To talk about the effect of such a black hole on Earth, it's best to start with something simple. For example, let's start with the appearance of the night sky. A black hole with stellar mass would have a bright accretion disk surrounding the black sphere, creating a very beautiful spectacle. You might have seen this kind of image in an illustration, science fiction movie, or computer game, but please forget about the image this time, as it doesn't apply in the case we are discussing, as I mentioned earlier. Black holes with masses similar to the Moon are very small. They have a strong gravitational force, but they are so small that at best, we can only see faint patches in the sky on a regular basis. In the worst case, it may not be until the space age that we realize the existence of black holes. Instead of solar eclipses, we may observe the sun through a gravitational lens caused by a black hole. Light passing through the side of a black hole is distorted by its gravity. Therefore, when the Moon passes between the sun and the Earth, we can briefly observe a faint distortion on the solar disk. Also, when the Moon is between a star and the Earth, the star that is the source of light appears differently to us due to the lens effect, such as appearing to emit momentary flashes like some other stars, or appearing to expand slightly. However, because black holes are so small, we can observe these phenomena only through high-performance telescopes. There is a deep connection between our culture and the moon, historically. The first calendar was likely the lunar calendar, no matter when it was made. The periodic changes in the size of the moon can be easily observed if there is only 1 month, but it is difficult to calculate it in areas where there are only rainy and dry seasons. If the moon were to become a black hole, the spirits would naturally become unknowable. This would cause a significant delay in the development of not only astronomy, but also civilization as a whole. In reality, time would only be measured in day and night, and it wasn't until the Stone Age that the concept of a year could be recognized. However, this is a story of when the Earth could somehow escape the destructive effects of a black hole, which may be quite difficult. As I mentioned before, this is the story of the eternal end. When a black hole appears nearby, it is very small compared to the many major changes that occur. As you know, it also affects the Earth's gravity, not just cars, but also constantly swirling to prevent other parts of the Earth from cooling down. Even if there is a black hole instead of the moon, there will still be tidal effects on the Earth, but because of its small size, the tidal effect appears to be concentrated in a narrower range and at a pinpoint. However, it will act more strongly. Near the equator of the Earth, natural disasters such as volcanic eruptions or earthquakes will occur intermittently. As a result, life will become practically impossible, and there will be a significant impact on the Earth's climate. Due to this geological activity, the Earth is getting warmer, and the transparency of the air is decreasing due to the continuous emission of volcanic ash. Earth will become darker and hotter in such an environment. Before we even consider whether humans can be born in such a scenario, it is unknown whether life can survive at all. It is entirely possible for Earth to become like Venus. Another problem is radiation emitted from the Earth's satellites. Black holes, in particular, emit severe radiation from their accretion disks. In this case, interaction with solar winds and the moon's magnetic field may also occur. Perhaps the Earth will be bombarded with constant streams of various particles, and it is unknown whether the Earth's magnetic field can protect it. If it cannot, after hundreds of millions of years of radiation exposure, all of the Earth's water will decompose due to the radiation's influence. Without radiation protection suits, the Earth will become an endless barren wasteland where nothing can survive. Of course, in such a scenario, no form of life could exist. Finally, there is a phenomenon called Hawking radiation, which suggests that any black hole will consume energy and mass over time and eventually evaporate. Particle pairs are created and evaporate, which is a very gradual process. For a stellar mass black hole, it would take endless time with dozens or hundreds of pairs sticking together, while a black hole with the mass of the moon would take only billions or trillions of years. In theory, the smaller the mass of a black hole, the more actively the particles mentioned earlier are created, causing another problem for us. As the particles rain down on Earth, they create confusion in the magnetic field and cause geomagnetic storms one after another until the last one explodes and dies. Of course, that is if it hasn't been swallowed by another black hole by then. There is also a theory that there are many small black holes in the universe, which are considered as one of the candidates for the role of mysterious dark matter. These black holes are thought to have emerged after the Big Bang because they have certain properties that satisfy the matter and space. If this hypothesis is correct, theoretically, it is also possible for Earth to have such a satellite. Lastly, there is something I would like to say. The possibility of such satellites being born in the solar system is low. In such cases, black holes will swallow all matter in the gas and dust cloud phase and grow to become a normal mass black hole. However, there is a good chance that they may come from somewhere in a completed star system far away. Certainly, there has never been a similar phenomenon observed in an alien planet. Therefore, the possibility of such an event occurring seems low.